Hello students, I am Dr. Tanmoy Biswas. I welcome you all in my channel Chemistry, the Mystery of Molecules. Today's topic of discussion is a very versatile famous reagent N-bromo succinimide or NBS. So this is the part of organic reagent series. So today we shall discuss the basic idea about this reagent, its preparation, properties, how it behaves, its application, chemical reaction, and very briefly NCS means N-chlorosuccinimide, NIS means N-iodosuccinimide, and one MCQ. But before going to details, I want to give you the MCQ and I request you please pause the video, try by yourself, and whatever answer you get please write in the comment box along with few words as explanation. Don't worry, at the end of the discussion you will get the right answer with explanation. So let's start. Now, if I say the basic idea, this NBS is actually a versatile reagent for synthetic organic chemistry. Why? This NBS could be broken down to produce the succinimide, you may consider anion and Br plus, and bromine being a halogen carrying positive charge, so you can consider it's electron deficient, that means it is an electrophile. So it could be used as a source of electrophile generation. And further, if you use radical condition, means then homolytic cleavage, means heat or radiation, then homolytic cleavage occurs. So this side, this arrow broken down, and another side is broken down and produce bromine radical. So it's a source of both cationic bromine and radical bromine. That's why it is so much unique in organic chemistry. And furthermore, the stability of these part, the anion from succinimide by resonance, that plays the important role for this uniqueness of this reagent. Why? Because this negative charge could be stabilized this way. So one canonical form you can draw, this is O minus double bond in this. There could be another canonical form also, I'm not doing. So two equivalent canonical forms stabilizes this anion from this NBS, which makes this reagent very unique, and it is the byproduct. So stable byproduct means electrophile will be generated so easily. Now you can see this thing very easily. So here bond polarity, if you look at this NBr bond, polarity is little different, because if you look at the electronegativity value of nitrogen and bromine, nitrogen is more electronegative compared to bromine. So consequently this NBr sigma bond is polar, and the polarity, nitrogen have delta negative and bromine have delta positive. Delta positive means electron deficiency, which makes this reagent electrophilic. So that's why you can see it acts as a good electrophile in nature. And by the way, if you compare this thing with another very known compound, succinimide, I guess you have studied Gabriel thaliamides, it's a similar type of chemistry here. So this succinimide NH is significantly polar. This is delta positive, this is delta negative, and treatment of base generates this nitrogen anion. What message I want to give? This generation of nitrogen anion is easier, which is stabilized just some time before. I have shown here the example stability of this anion, and that's why this is acidic. Similarly, this reagent NBS is a good source of bromine electrophile. Next, now if I say preparation of this reagent, how it is prepared. Sometime before I have told you regarding the acidity of this. That's why if you treat this reagent with sodium hydroxide means OH minus, here acting as a base. So what it does, it abstracts this proton and produces this anion. So fine, this anion is produced. This is N minus, and obviously water is there, I'm not going. In the second phase, what happened? It reacts with bromine, because we know bromine could be polarized into delta plus, delta minus, and this delta plus part is attacked by this nitrogen anion, which is acting here as nucleophile. So it will open up and finally produce this NBr, and obviously HBr, another part, which in presence of NaOH will be converted into salt and water. And by the way, this reaction is carried out at low temperature, 2 degrees centigrade to RT, because after this reaction, from this reaction medium, these NBS, pure NBS is actually collected by crystallization. And remember, crystallization results a pure product. So that is a strategy to obtain pure NBS, which is very important for organic transformation. Furthermore, one interesting point, why low temperature? If you think, if you increase the temperature, there is a chance of this amide hydrolysis. This bond could be broken. How? But OH minus can act as a nucleophile and attack this carbon center. So further amide hydrolysis is possible. So low temperature stops that reaction chance. And furthermore, you may think, sir, sodium hydroxide, bromine, you are talking about carboxylic acid amide. Why not Hoffman degradation reaction occurs during these NBS preparation? By the way, student, for this purpose, we need primary acid amide. Okay, means this nitrogen need to have two proton attached, primary amide. By the way, during discussion at the end, you will find one example where I shall explain about this thing in details. So remember, since this Hoffman degradation requires primary amide and this NBS is not a primary, this nitrogen is actually a secondary nitrogen, so it's a secondary amide, because if you look at here, this is secondary amide, nitrogen is attached to two carbon, so product from this secondary amide, this NBS, cannot be hydrolyzed under this reaction condition, so reaction will stop at here. Now if I want to go to properties, the simple thing, N-Br bond is not highly stable. Why? Both are electronegative atom and there is a size mismatch. Why? Nitrogen, bromine, if you compare, nitrogen belongs to the second row and bromine belongs to the fourth row. So there is a orbital mismatch, orbital size mismatch. And if there is a orbital size mismatch, so you can expect the bond is not stronger, because bond overlap will be less, bond will be weaker, so it will be more reactive undoubtedly, and consequently its breakage can result in bromine plus under normal condition because of polarity. As I said, nitrogen is more electronegative than bromine. Next, upon heating, if you heat this reagent, since this NBr bond is weaker, as I told, undergo homolytic fission to produce bromine radical. So it is actually a dually beneficial. It can result bromine electrophile generation as well as bromine radical generation, and that is all possible. This bromine electrophile generation, as the nitrogen anion or leaving group is doubly stabilized by two carbonyl, two adjacent carbonyl, so two equivalent canonical form I have shown just some time before. Now if I utilize this reagent as laboratory reagent, then two ways we can utilize. As I told just some time before, it could be used for generation of electrophile for bromination reaction, or it could be utilized as an oxidizing agent, since just look at bromine is carrying a positive charge, means it is an electron deficient. And if I say halogen, halogen is actually, it should be electron rich because their electronegativity is generally higher, they prefer to be Br minus. So how bromine can be Br plus to Br minus? Obviously by accepting electron. So if it accepts electrons, then it means that it takes electron from someone else, so consequently it is acting as an oxidizing agent or oxidant. So that's how these NBS can behave as oxidant. I shall give example during this discussion too. Now first example, preparation of bromohydrin. What is mean by bromohydrin? It is actually you can consider bromo alcohol. Actually there is a term called halohydrin, so this is a very common, since here we are using NBS brominating agent, so that's why it's a bromohydrin. This NBS act as a source for bromine plus, so that bromine plus react with this alkene, and we know that bromine electrophile result in a bridge bromonium ion generation. Okay, so that's a very common thing, and under this reaction medium it generates obviously a cation. So this is Br, and this cation is actually a secondary cation, so relatively more stable, and in the next phase water molecule attack as nucleophile and ultimately result in this alcohol. So that's why 1:1 water THF there. Remember student, this reaction is very interesting, this bridge bromonium ion 3 member ring formation. By the way, I have already discussed a dedicated lecture, please visit the comment box or I button. Now here remember one important point, halohydrin, a liquid equivalent to epoxide, I shall explain. So that's why remember epoxide, if I say ethylene oxide or any propylene oxide, so they are gaseous in nature, so their handling is difficult, furthermore explosion chance is there. So in order to avoid this problem, these epoxide could be converted into halohydrin, or they could be transported, and whenever needed they could be generated from this halohydrin. How? So if you treat with any base, so like sodium hydroxide or potassium hydroxide, so what hydroxide will do? Hydroxide will abstract this proton, so this proton gone, O minus. What this O minus will do, it will attack intramolecular SN2 type reaction, backside attack, so it will produce the epoxide later. Okay, so this is a way to generate epoxide by two steps. And how can you convert epoxide into halohydrin? Obviously add, for example, in this reaction you can add HBr. So that's a very interesting methodology. And by the way, student, what should you choose, NaOH or KOH? If I say NaOH, that is a cheap. If you say KOH, it is relatively costly, but its solubility more in organic solvent. So based on your reaction condition, you choose the particular reagent. So in this way, these NBS could be very useful for preparation or transport of epoxide from alkene via halohydrin. Okay, so let's go to the next reaction. Anti-addition to alkene. By the way, student, just last example we have studied that if you react with this alkene with bromine plus, what it will produce? It will produce a bridge bromonium ion, 3-member cyclic molecule, and later on it will react with F minus, and these attack, it's a SN2 type reaction, backside attack, so it's a result in an anti-addition. Okay, so that's a thing. Now question, why fluoride attacks, why not triethylamine? By the way, first of all, triethylamine, if you look at these molecule, because of this 3-ethyl group, this molecule is bulky, and this is considered as specific proton scavenger. Means it can very easily act as base rather than a nucleophile. By the way, I have already discussed a dedicated lecture on specific proton scavenger or selected base. You may visit for learning. So it can act as a base. And if you look at HF, HF is, by the way, as a weak acid. So what it can do? It can produce one H plus, and that will be consumed by this triethylamine. So it's a protonated. So free fluoride ion is there, and that fluoride ion is acting as a nucleophile here to result in this product with an anti-orientation. So this could be another way for student CF bond formation. By the way, these you can consider nucleophilic. So nucleophilic CF bond formation reaction. So this is a very interesting, because carbon fluorine bond is very important from synthetic chemistry point of view. And by the way, I have already discussed few lectures on carbon fluorine bond formation. Please visit. They are very interesting, and future perspective wise they are very important too. Next, alpha-halogenation of acid chloride. Carboxylic acid chloride here taken, and NBS HBr carbon tetrachloride 85 degrees centigrade. Means it's a, you can consider boiling condition or effluxing condition with carbon tetrachloride. So in this case, the reaction proceeds through enol as intermediate. How? HBr is there, strong acid, so it will protonate this carbonyl carbon. Later on, it undergo enolization easily. So this is the enol structure, and these enols are very much electron rich. Why? Because there could be one resonance, it can open. So you can consider, you can see here that negative charge is here, double bond OH plus, and obviously Cl. That's why this center is actually student nucleophilic. So these will react with NBS, obviously, I mean bromine plus or bromine radical, both formation possible under this temperature condition. So if you take any of them, ultimately it will result in this product. Why? Because enol is nucleophilic, and it can react with both Br plus and Br dot, same product, that is alpha bromination of acid chloride. Okay, so this is a very interesting reaction, and in this case, as I told, enol act as intermediate, so, and it is acting as the nucleophile too. Next reaction, if I say NBS mediated Hoffman degradation type, as I told, this is very interesting. So if you take, this is actually primary amide, okay, and DBU, it's actually an organic base. So you can see how it can act as base, student. So these nitrogen will be protonated. So nitrogen H, this part I am not focusing, this is carrying positive charge. So next canonical form, this lone pair will come here, it will open. So it's a, you may consider it's a delocalized protonated structure, so that will be stable. I should not say equivalent canonical form because it's not exactly same, but in this way you can accept. So it's a stronger, significantly stronger organic base. So NBS and base, what it will do? First base will generate, so I am taking this part as AR. AR C double bond O, you can consider NH minus. Later on this minus will react with NBS, bromine as electrophile, so it will be quenched as NBr. Now in the next step, DBU can act as base again, and by the way, right now the acidity of this proton enhances. Why? Because electronegative Br attached to nitrogen. So when it goes, it produces again another anion. Second step. So in this step, what it will do, this Ar will migrate here. Ar will migrate, Br will leave, and ultimately the lone pair will come here. So in this way, what it will produce, Ar bonded with nitrogen, that nitrogen form a double bond with C double bond O. So this is, student, isocyanate. So in this case, this isocyanate carbon act as electrophile, and here methanol is there, which can act as both solvent as well as nucleophile. So in the next step, it will attack, it will open up, come back, and this bond will open up. So ultimately product will be this NH. This is actually, you may see amide ester of carbamic acid. So this part is ester and this part is amide. Now you will say, sir, Hoffman degradation generally result in amide, sorry, primary amine with a one carbon less. Why amide? Why this amide is here? By the way, student, if you take this molecule and if you treat it with strong base like sodium hydroxide and heat this, it will generate in this molecule. That's simple, just this amine. Okay, so this is the uniqueness, but since here methanol is taken as a solvent, so that's why it produces this product. So reaction is stopped here. I guess it is clear. So you can say this DBU act as a base, Br plus electrophile is generated from NBS and produces, this is next. As I told sometime before, second point, that oxidizing agent. So here if you take any amino acid, this is most typically say alpha amino acid, so it reacts with NBS. Now NBS has a bromine plus and it reacts with these NH2 lone pair, and what it produces? It produces this bromo derivative, R, obviously carbon NHBr. Now carbon hydrogen double bond OOH. Now one question may come in your mind, that why does NBS brominates primary amine? Because NBS means there is a nitrogen bromine bond. As I told sometime before, this NBr bond is not stable, but here also one NBr bond is produced. Question, why this is? What is the driving force for this reaction? Student, if you look at these nitrogen, if I say this nitrogen is attached with two carbonyl group which are electron withdrawing in nature, so you can expect the nitrogen lone pair have some delocalization in both of this carbonyl group. So resonance stabilization, fine. Consequently, I can consider that this nitrogen is electron deficient. But if you look at amines, this amino acid, if you look at these NH2, it's a primary amine, 1 degree amine. So primary amine, and it is not attached to any electron withdrawing group, simple carbon. So it is not that much electron deficient. So our electron rich nitrogen is attacking, and product, if I say the nitrogen, the succinimide anion, that is resonance stabilized, I have shown sometime before with this conjugation with this two carbonyl group. So that is the driving force. I am not focusing on this NBr bond, but the final product, that is these anion which is produced, that is relatively more stabilized. So reaction happens. Next phase, these part undergo means you can consider intramolecular reaction. These NBr bond broken, as I told, it is not that much strong, so it broken down. This oxygen means here from this part you expect HBr formation. Now this bond goes, by the way, it opens up, comes back and undergo decarboxylation. So from this part you can expect carbon dioxide, fine. And whatever this bond was remaining, it comes and produce this imine. So just look at here, it was a primary amine and it is oxidized into imine. So that's why it is, I am saying that NBS here acting as an oxidizing agent. And NBr bond is why not stable? I guess I have explained, because of the orbital mismatch, size mismatch. Now next is the NCS and NIS, very brave for discussion. Now, if I say N-chlorosuccinimide or NCS here, it is actually you may consider the chlorine analog of that reagent, and in this case here actually NCl bond is there, and it is also the similar polarity like the NBS, and it can act as a potential source of chlorine plus. Similar thing you can expect for N-iodosuccinimide. By the way, this bond is far more polar compared to this and very weak because size mismatch. Iodine is even bigger than chlorine. However, chlorine is shorter, smaller than bromine. So from that point it's okay. But iodine is bigger, so this bond is far more weaker. So N-iodosuccinimide reagent is used in organic chemistry for the iodination reaction of alkene. By the way, for chlorine, chlorination, so you can expect chlorination. For iodine, it's an iodination. So it is actually a mild oxidant too, as I have explained in case of NBS. So NIS is the iodine analog of NCS and NBS too with similar properties. So this such reagent possible exist. Now, so I guess we have learned a lot. So in conclusion, NBS is actually a good brominating agent, and this reaction occurs by electrophilic bromination pathway generally under normal condition, and this NBr bond is actually weaker because of improper size matching or overlap between the orbital, means second and fourth row element, and further the polarity and electronegativity which resulted polarity in the bond makes this reagent further less stable. And as I told this, when bromine acts as electrophile, so what is left? Succinimide anion, which is doubly resonance stabilized, which allows the Br plus to leave, means Br plus can act as a good electrophile because of this. And if you use under heat or irradiation, then it can produce bromine radical too. So that radical can undergo electrophilic addition, or it can undergo radical substitution like allylic substitution. By the way, student, the next MCQ is related to allylic substitution. I shall explain. So this is halogen. So it is actually in -1 oxidation state bromine prefers, and that's why NBS, and in this case because of electronegativity difference we can say bromine is in +1 oxidation state. So NBS can act as oxidizing agent too, which results in bromine minus, stable form of halogen. So that's why it can act as oxidizing agent too. Now let's go to the MCQ. I guess you have tried. It is a very easy example. What is the major product of these reaction? 4 options are given. Student, if you observe this, it is NBS, carbon tetrachloride. What is this molecule? This is benzoyl peroxide. More accurately, if I say it's a dibenzoyl peroxide. So PHC double bond O, again C double bond. By the way, there is a mistake. It's not like that. This one oxygen will not be there. This is PH, dibenzoyl peroxide. What it does, it undergo breakage, homolytic fission, refluxing condition. Reflux means boiling slightly higher temperature than the boiling point of the solvent carbon tetrachloride, and CCl4's BP is 76.72. You can expect sir 85 or 90 like that temperature. So 2-hour reaction time. So under heating, this bond broken down homolytically resulted in PHC double bond O dot 2 radical. In next case, what it does, next case this bond breaks. So one electron comes here, one comes here, and it produces 2 molecules of phenyl radical plus another molecule, 2 molecules of carbon dioxide gas. Fine. No issue. So here radical is generated by these dibenzoyl peroxide. Fine, we understood. Now next phase, what happened? This radical reacts. Now radical has 2 chances. It can do addition with this alkene, or it can react with this allyl halogen. By the way, there are 2 allyl hydrogen. So you can say this is number 1, this is number 2. And how reaction happen? These allyl hydrogens, so you can expect this reacts with pH radical, and it can generate another radical, allyl radical. By the way, allyl radicals are resonance stabilized. How? So one can come here, one can come here, one go. So in this way it will produce another radical. So anion radical are relatively stable. Radicals are actually very reactive species, but some stability there because of resonance. Now what this allyl radical will do in the next step? so you can expect in next step it will react with this NBS, NBr bond. So in this way it will capture this bromine and ultimately produce allyl bromide. Okay, and obviously nitrogen radical again. So in this way reaction will continue unless reagents are consumed, for example NBS consume or so that's the thing. And this reaction is very quick, that's why you see 2 hours is enough for the completion. Now question, sir, there are two allyl positions. So allyl position 1 is here, allyl position 2 is here, where the reaction is expected to occur. Now if you consider here the radical is more stable. Why? Because both are allyl, agree, but this is a secondary student, so there is another alkyl group which can provide some more stability, so that's why reaction will prefer here. So that's why option A is the major product of this reaction. Okay, now these two option A and B logical, but if you look at these C, radical combination not likely. And this is a bromine addition. By the way, I haven't taken any bromine molecule, I have taken bromine electrophile. So from where the nucleophilic bromine will come? So first is electrophile, agree, second nucleophile, not possible, illogical choice. So you may have confusion between option A versus B, and the logic is that this option A radical is relatively more as it's secondary allylic. So these will be the product. So this is the end of discussion, student. Thanks for watching. If you really enjoy my content, help my channel to grow, and you can visit 2 of my other channel. Stay happy, stay blessed. See you in my next video. Bye bye.